Well, welcome back, ladies and gentlemen. Let us move on. We are talking about E cells, E prime cells, the standard cell potential, and we've done some pretty simple problems with that. Now let's get on with some others. Okay, so now it's really not hard. We're just putting together a puzzle now. I have a voltaic cell. If I have a voltaic cell, that means what? That means that it is a spontaneous process, which means my standard cell potential must be positive. So then I've got two possibilities. I've got cobalt, right? I have cobalt going to cobalt 2, or I have, this has got to be an H plus there, by the way. I have, no, maybe not, sorry. I have silver chloride going to silver. So how am I going to figure out which of these is at the anode or the cathode? Well, I'm going to look at my standard reduction potential, right? Because what do I know? I know that the one with the higher standard reduction potential is going to have to be what? At my cathode, meaning it would be my half reduction reaction, and the one that is less positive or more negative is going to be at my anode, which means it's going to be my half oxidation reaction. So all I have to do is go back and look at my table, and I'm looking for, let's clean this up a little bit. I just love being able to take care of all my mistakes that way. Yeah, if only I could have done that with my relationships, right? So I'm looking at cobalt. Cobalt is, do I have 2 or 3? I better look because there's a 2 and a 3. What is it? Oh, cobalt 2. Cobalt 2, cobalt 2. So I have cobalt 2, and so that means I have a negative 0.277 for my cobalt, right? And the other was what? Ag going to, AgCl going to Ag, ooh. I'm almost too small to get that right up there. There it is. And that's a positive. That's a positive 0.222222. All right, good. I can answer this now. Here we go. So, what did I say? My higher one is a 0.222. So that means my silver chloride, silver is going to occur at the cathode specifically. Sorry about that. Specifically, what's that reaction? Yoink, let's go back. It would be AgCl solid, right? Going to Ag solid plus Cl. Let's go back and see that reaction. Ag plus Cl minus, oh, and an electron, of course. What am I thinking about? I forgot that this is actually doing what? Reducing. Good. There we go. And then what is happening at the anode? Well, the anode is a simple one, right? I have my CO solid going to cobalt 2, aqueous plus 2 electrons, right? And there we have it. Now notice here, how many electrons do I have here, right? I have 2, so I'd have to multiply this by 2, right? So if I were going to write my balanced equation, it would be CO solid plus 2 AgCl solid going to 2 Ag solid plus 2 Cl minus aqueous plus CO2 aqueous, right? Because then I'd have 2 electrons cancel here and here. Good. Now, when I do my Ecell, what do? I take my standard reduction potential at the cathode, which we said was 0.222 volts, minus my standard reduction potential at the anode, 0.277, and so that would be equal to what? How about 0.499 volts? Notice what I did not do. Even though I multiplied this half reaction by 2, did I do anything with my standard reduction potential? The answer is no. And why is that? Because as I said in the notes, the uh, standard reduction potentials are intensive. They do not depend on amount. So here we go. This would be my standard reduction potential for the cell. It's greater than 0. So then my galvanic cell does, in fact, function as a galvanic cell. All right. You guys try this. Let's see. Assume blue, blue, blue. Yeah, try this one on your own. See what you can do. All right, bring me back here. I hope you brought me back. Um, what am I going to do here? I look at this thing and I say, it's not exactly what I did before. What might I do? Well, they give me the standard cell potential, and what do I know? I know that my E cell is going to be equal to the standard reduction potential for whatever's happening at the cathode, which would be also whatever is my half reduction cell, right? Minus E reduction at the anode, right? Good, or my half oxidizing, right? So what do they give me? Says here I've got this. They can tell me aluminum. I want to know what it is for my iodine. So I have to look at this reaction, and I have to say what is oxidizing and what is reducing. It looks to me like aluminum is going from a 0 to a +3. So the aluminum must be oxidizing. So that is oxidizing, which means my I2 is my reducing species. So this means that this is happening at my cathode. This must be happening at my anode. And they give me, in this case, my standard reduction potential, saying that 2.20 volts is equal to my standard reduction potential for my I2 minus my standard reduction potential here at the anode, which would be a negative 1.66 volts, right? So what do I get out of that? I'm going to take a 2.20 and I'm going to subtract my 0.166, right? Because, ladies and gentlemen, this would really be 2.20 is equal to my standard reduction potential. A negative minus a negative is really a positive 1.66. So how do I get rid of the negative? I have to do this, right? Subtract. Yeah, you guys remember math, basic math. Fox would be so proud of you all if you can handle this. And you get a 0.54 volts. So that's what my standard reduction potential, 0.54 volts, would be for iodine. Let's just see if we are right on that. We have a table, and let's see what the table says. Okay, iodine, iodine, iodine. Ooh, where's iodine? It says that my iodine is 5.36. And what did we say? Doot, doot, doot. 5.4. Hey, yeah, so when you round it, we got the right answer. Great. Let's see if there's another one for you guys to do here. All right, you guys try this one now. Cool. Okay, so what would we do? First thing we have to figure out is what's oxidizing and what's reducing. I've got indium going from a +1 to a +3, so that would imply to me that my indium is oxidizing. And then what is reducing then? It better be my bromine. Okay, so what do we know? We know that my E prime cell is equal to E, the standard reduction of potential for my reducing species, minus the standard reduction potential for my oxidizing species. And what do they say that is? 1.46 volts is equal to, we said my reducing species is my bromine, right, minus my standard reduction for my indium, right? And they give me what? Do they give me? Oh, I guess I'm going to have to look up both of these, or I can look up bromine from my magic table at least, right? Where's my magic table? Magic table, magic table. Bromine, where's bromine? There it is. 1.065. I better write this down. I'm going to trip too over my own headphones. 1.065 volts. Yeah, if while this goes on, you hear a thud and then no sound, that means I've fallen and I can't get up. Please call emergency and have them come get me. Now, I hope you watch this, within the year. If not, I might be laying here underneath my desk for several years before someone finds me. 1.46 volts is equal to my bromine. 1.065 minus my standard reduction potential of my indium, right? My indium, I guess, indium 3 is what that would be. Okay, so then I subtract 1.065. I think I can do that in my head. It might be tough. Make that a 5, make that a 10, make that a 5, make that a 3, make that a 1, make that a 9, make that a 3. How about a 0.9395? But really, I don't get that many sig figs, so I'm going to go with 0.40 volts. Lindsay, can you check me out to make sure that's right? I don't hear any Lindsay responding to me. Where are you, Lindsay? Can I not rely on you anymore? What is that? So I guess you're going to make me use my calculator to make sure, because I'd hate to make silly mistakes. Woohoo! I made the right. It's right. I can do mental math with simple subtraction. That makes me feel so good. All right, there you go, ladies and gentlemen. Okay, wonderful. We have really about one more question here, or two maybe, that I want to answer before we move on to a new concept, and then we'll end this before I go to the new concept. Which is the better oxidant? All right. We could really go back and add one more concept to our notes. You ready? I hope this doesn't make you car sick by this moving so fast. Yoink, 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 yoink. There we go. And that is that my standard. Woo. Okay. My standard reduction potentials are related to oxidants, oxidizing agents, right? And it's a pretty simple idea. The higher the standard reduction potential, the more likely the substance will reduce, which means it will cause something else to oxidize. By the way, that is an A. That's a funky A, not a 9. So substances with high standard reduction potentials tend to be good oxidizing agents. Oxidizing agents. Great. Cool. So, remember, I gave you a list of some oxidizing agents. Let's clean this up again. Ooh, I don't really like that yellow color. I'm not a big fan of mustard. And maybe you'd call that mustard or goldenrod. I'm not sure that's a really pretty color. Give me a brighter, like a maize. Maize goes so nice, especially with blue, right? Maize and blue, wonderful colors. Okay, we were talking about if you look at higher standard reduction potentials, these things tend to be good oxidizing agents. And so we said something like dichromate here, 1.33. By the way, that is wrong. It should be Cr2O72 minus, not Cr072 minus. What else did I say? I said what? Permanganate. Where's permanganate? Ooh, look at that, mama. 1.51. That is a high standard reduction potential. And then I said what? Oh, holy moly. Look at this. My hydrogen peroxide, 1776. So those all tend to be very strong oxidizing agents, and it's revealed through their standard reduction potentials. So then, which of these is a better oxidant? Well, what am I going to look for? I'm going to look for their standard reduction potentials. So I want to know bromate and iodate. Bromate. So bromate, where's bromate? BrO3 minus, where's bromate? BrO3 minus is a 152. 152, I have to write this down. 152. And what is my iodate? Iodate is a 1195. 1195. 1.195. So I have a 1.52 volts versus a 1.195 volts. Well, this is bigger, so it is the better oxidant. That's simple. Cool. Okay, you guys rank these according to the oxidizing strength. Bring me back in a sec. Oh, in case you don't know, I have uploaded a copy of the standard reduction potential to Canvas, so you can use that. All right. Oh, so what am I going to do? I want to look at these. I need to figure out my standard reduction potentials for these. And specifically, I need standard reduction potentials for Ag plus, for our Cr2O72 minus, and for NO3 minus. All right, here we go. Silver. What is silver? Ag plus. So, oh, by the way, here's dichromate already. So dichromate is 1.33 for dichromate, right? Cr2O72 minus. What's my Ag plus? My standard reduction potential for silver is 0.799 positive, 0.799. That's my Ag plus. And then my nitrate, NO3 minus. Nitrate would be, that looks like nitrate, right? 0.96. 0.9, is that right? 0.96, yeah, for my nitrate. And so that's pretty simple, right? This is the highest, so it's going to be dichromate is going to be greater than nitrate, which is greater than silver plus, right? Because this is 1.33, this is 0.96, this is 0.799, right? Cool. Piece of cake. This is easy as well. I already mentioned this multiple times that standard reduction potentials don't only affect galvanic cells, but all redox. And so we can just simply, ooh, I need to change colors. Give me a new color. How about that color? How's that? Good. So my standard reduction potentials, that's pretty ugly color, but that's okay. Excuse me, we're no longer in a cell, so a standard reduction for a redox reaction. And well, maybe we need some notes. Let's go back to notes for a second. All right, that's A, B, 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 C, D. Yeah, let's make it E. I think E would be fun. I got to go back to the yellow, don't I? E. Let's go with E. Let's go with E prime and redox. All right. So I can use my standard reduction potentials. Well, let me rephrase that. My EMF is not just the driving force for galvanic cells, but really it's valid for all redox, right? And so what we do then is we will calculate a standard E for my reaction, which will be my standard cell potential, standard reduction potential for my reducing species. And that's not, remember, reducing species is not the reducing agent. The reducing species is the thing that reduces, minus my standard reduction potential for my oxidizing species. Oops, species. Good. There we go. And now here's the thing about it. I'm going to make this an A. If my Ecell reaction is greater than 0, then my forward reaction is thermodynamically favored. Ach du lieber, you mean you are bringing in thermo with electrochem? Yes, absolutely. In fact, I probably should have changed that. Yeah, I think I will. I'm going to make you all mad, especially. Well, no, I won't. I'll make a new Roman numeral in a second. For my forward reaction is spontaneous, right? Good. B, if my E prime reaction is less than 0, then my reverse reaction is spontaneous. And oh my Güte, can you believe that he is actually going to do this and not just bring redox in to play with thermal, but also with what? Equilibrium. If my E prime reaction is equal to 0, I am at equilibrium. Ah, cool. You know I'm going to have a lot of fun with that, don't you? Yeah. Maybe I should not say that. I'm not so sure I want to say that. Let's not say that. I'm gonna back that off. Maybe I jumped the gun on that. Let's just stick here and say that if my if my potential cell if my cell potential for my reaction is greater than 0, the forward reaction is spontaneous, and if it's less than 0, the reverse. All right? Good. Now let's answer the question. Good. Here we go. I got to change my color pen. Zoink. I'll go with that instead. All right. So I need to identify what is oxidizing and what is reducing. I have copper going from 0 to +2, so that's oxidizing. And so I want to put my standard reduction potential for Cu2 plus here. And my hydrogen is reducing, so I'm going to put my standard reduction potential for H plus here, right? I know that is a 0.0. I should remember my copper. I think it's what, a negative 3.77, but let's go back and look. Copper. Copper 2 going to copper solid is a 337. 0.337 volts. And so what do I get out of this? I get a negative 0.337. volts. This is a negative value, so it is not spontaneous in the forward direction. Good. You guys do the next one. You do these three, all right, and come back. Okay, cool. All you have to do is we have to just look and check out these things. So what is happening here? My I is oxidizing, so that means my E for the reaction is going to be my standard reduction potential for my chloride minus my standard reduction potential for my I2. So let's look those up. Chloride, where is my chloride? Right here. It is a 1.359. What is it for my iodine? Oh boy, I have to clean up some stuff here because I can't see. Good. Iodine is right here, right? 0.536. 0.536. Okay, so I'm going to take my chloride, 1.359 volts minus 0.536 volts, and that is clearly going to be a positive value, and so it will be spontaneous. Spontaneous. Good. Now we need to look at the next one. What happens? I have manganese going from 0 to +2, so that means I'm looking up for my manganese 2+ reducing, and so my reaction is going to be then what's my standard reduction potential for my other one? It's going to be my H2SO3. So let's do that. H2SO3. What is my H2SO3? H2SO3. H2SO3. Hey, right here. So I have a 0.45. 0.45 volts, and my manganese 2 is a negative 118, right? Negative 1.18. So I have a 0.45 volts minus a negative 1.18, and that's going to be greater than 0, so that will be spontaneous. And then my final one, I have that's a 0 going to a +2, so my mercury is oxidizing, and that would mean my iodine is reducing, so my standard reduction potential for my reaction will be my standard, excuse me, my potential for my reaction is equal to the standard reduction potential for my iodine minus the standard reduction potential for my mercury +2. Remember, these all have to be reductions, so even though my mercury is oxidizing, I'm looking for what's happening on the other in reverse for the mercury, right? I'm looking for the Ag2+. Okay, where's my mercury? Mercury looks like mercury is a what? Going to mercury liquid, right? So it's a 0.789 volts. You guys agree with me on that? And what's my iodine? My iodine is a 0.536 volts. Good, so let's go there. And let's take a look. I said this was a 0.536 minus a 0.789. Well, that is a negative value, right? That is bigger than that, so that means that's less than 0, so it is not spontaneous. All right, cool. Good, let's quit. I hope you've had enough, because I certainly have. I need a break. My ears are about ready to blow up. All right, so I hope if you have any questions, just fire those to me. Right now, you can do it through the discussion board. All right, see you later. Bye.